Now we can submit this as batch script and wait until it will be queued and executed. Did you submit it already? Good. And at the end, you should, once it has completed, you should have something like this directory inside bin.scorp. Did anyone already got results? Okay. Just read the question and try to reply to this. Here, I'll try to give some questions at the end. Try to reply to this question. Let's wait a couple of minutes. So who knows already results on this question? Yes? What is it?
For me it was 48 seconds, so it's like 3 times the execution time.
Yes, yeah. So it means that the overhead of instrumentation is really huge, and we need somehow to reduce it. And to do this, we need to go to the next part, filtering. But let's wait 2 minutes and we are more or less on the same page. Who is still following me? Okay. 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 Yes.
Could you explain again what is user instrumentation is?
User instrumentation, if you, for example, want to mark a particular section in your software, let's say solve a loop. It's in a multiple function, but you want to combine it and see it in the profile, like a single region. It's user instrumentation. And for this, you need to modify your source code. At the moment, it's not enabled. Yeah, you can simply remove this -- user, but in general, if you would like to do this, you need to enable this -- user. It's basically what it does. It provides your compiler additional options to your compiler to set like set the headers, where the headers are located, set the path. But to enable it, you need to modify your application manually. And it's, again, depends on your, is it C, C++, Fortran. There is also in the reference material you can find how to do this. This is just to explore what is possible. But it's really handy. For example, you want to mark a loop. Loop won't be instrumented because what is instrumented is the function calls. But if you are interested in a particular loop where you spent a lot of time, but it's not in a single function, you want to mark it. Or you want to mark, let's say, 5th iteration of this particular loop. Then you have a special, like, if iteration equal 5, enable scorp. If it's 6, disable. That's it. And then it will be visible in the trace and also in the profile. Okay, now we got a huge overhead, and we would like to know what the cause of this. For this, we can do the scoring of our measurements. If you execute this command, scorp -score, you'll get the following information. So it means it's summary of our execution, and it gives our hints how much memory would we need for such a short run to collect the traces. And you already know it's 160 gigabytes for such a tiny, like 40 seconds run. And we also would need to know how much memory we would need per process to collect this information, and it's 21 gigabytes. This is scorp total memory. It's important value. We need to note it like later. Once we filter it out, this we would need to set to collect the traces. This is like necessary to know. Then we'll have a table with all the information. Like we have amount of visits, how much some particular events were visited, how much time is spent, how much time in percentage, and max buffer in bytes, how memory we would need to collect this data. And you can see all, it means like type is regions, and they all are divided like the breakdown. You can see all is all functions, MPI is MPI functions, OpenMP is OMP function, OpenMP function, COM is combined. It means that inside the function, let's say user function, we are calling MPI or OpenMP. It will be called COM. It's not user, but COM. Like something interesting is going on inside this function, and it will be called COM. User, it means like it's just user function, your written function. Scorpy, something related to Scorpy measurement system. Yeah. And if we look into results, we can see that the 21 gigabyte is necessary to collect some user data. It's not MPI, it's not OpenMP, it's not COM. It is pure user data. And we would like to know exactly, we need to get a breakdown, what's going on, and where we can actually get this overhead. For this, we will execute this the following command. Yeah, I hope you all follow and can get the results. And what is highlighted here, so basically you'll get a breakdown of all functions which are identified in your applications. And again, you will see the type, user, OpenMP, and so on. And you can clearly see here that these 6 functions, especially in these 3 ones, it was called 2 billion times. And time per visit was it's microseconds, 0.18 microseconds per visit. Per visit means per call. So basically nothing is going on in this function. And we might not interested in this function. So this is a very good candidates for filtering this 4 functions. Yeah. For example, in C++ application, it would be the case. You'll have millions of tiny get or set functions, and you would never want to measure them. Probably, like if you are not particularly interested in get or set function. But this is a good candidate. How here I am showing how you can identify the candidates. Okay, we identified the candidates, and now we can prepare a special file to filter these particular functions out. Let's scroll this long file. Here's a typical filtering file. So basically, you can create your own, but no worries. I prepared one filtering file for you. You don't need to worry about this. So basically, what's the structure of this file? We basically said that we set the region name. So we want to exclude functions. And we want to work with function. And then we say what we want to do with them. We want to exclude them. It's also possible to include. For example, one handy case which I use exclude everything. You can use asterisk, for example, exclude everything, and then include only 1 or 2 functions what you're interested in. Very handy, in my opinion. Yeah. Similar, you can like have multiple blocks. The Scorpio will analyze it in a loop, and then the last one will be valid. This similar process can be done for function for file names. You can exclude also file names. Yes.
Slightly off topic, but you mentioned so something like get and set in C++. So if functions are inline, do they still appear in these traces?
No, it's yes and no. Like it depends on the compiler. Typically, you won't get inline functions. So the question was if the inline functions will be appeared in the profiles or in this scoring. The answer is tricky. You never know. Basically, in GCC, for example, they won't be appeared. If you want to appear them, you can also enable some compiler flags to disable inlining. Also, you can set a score p verbose variable during compilation, and then it will be shown what will be enabled and what will be disabled from the measurement. But sometimes you can also push what will be enabled and what was disabled with the verbose output during compilation. Yeah. The similar process you can do with file names. You can exclude some files, include some files, and so on. And all this can be in a single file, filtering file. Now we would like to simulate what will happen if we apply this particular filtering file. For this, you do the following: score p score minus r, and then minus f in the path to the filtering file. And then you'll get a simulation what will happen if we apply this filtering file. Did you follow? Break? Break time.
Well, just finish whenever you can. Just let me know.
Let me finish this filtering part. Yeah. Is it? No, it's half an hour more, I guess. Okay, no break, sorry. Did you get results? I hope, yeah. And here you will see if the functions was filtered or not. If the functions will be filtered, you will see the plus. If not, it will be minus. A bit confusing, agree? But you will see that, okay, these 6 functions will be filtered out, yes? And as a result, you can see that for collecting the traces, we already have a manageable amount of memory. It's 661 megabytes, much better than 160 gigabytes. And in this case, we will need 95 megabytes to collect the traces. Remember this number, we will use it later. Yes. Now we would like to apply this to our batch script. For this, to apply it for the batch script, you need to modify these 2 lines, go to the batch script, and modify these 2 lines. So basically, you put underscore field here, so we don't want to overwrite our measurements. We put it into the new directory. We put underscore field, and we also enable filtering file, like this. We set a particular variable, show where the filtering file is located. And this is only 2 changes in the batch script. And you can submit it. Like, it's usually a little bit longer, like.
No, compared to that, it's longer than the baseline, but only a bit shorter than the full trace.
What was your original one?
The original one, there we go, it's 49, and then it was 48 seconds.
Maybe then it didn't apply the filter, I guess. So basically, you should check if this file exists. This -- config score p field. The file should be existed, and you have to submit it. You have to check that you apply the filter. Like this one line should be uncommented. You probably still have hash, no? Okay. Anyone else have measurements already done? Yes? You done? Okay, so this is what I expect. Like it's still some overhead, but it's much faster. So basically, the rule of thumb is about 10 to 20% overhead is acceptable. What is beyond is not necessarily acceptable, but for example, it is acceptable if you want to learn how your application runs. If you have a community code and you have no idea how it works, then you can collect full profile, examine how it works. You don't care about overhead. But if you want to do a performance measurement, then you can.
Now we created a filter after running it once with the full analysis. Is there a good way to exclude some part of the code beforehand? For example, the code I'm working on has a huge initialization. I don't really care about it.
Yes, the GCC, for example, provides, not all compilers provides, but some compilers you can exclude during compile time.
Okay, so in the source code I need to annotate.
Yes, yeah. So basically you provide filtering file during compilation, not during runtime. Like now we are doing it during runtime. And you can also, in the filtering file, you can use also whitelisting, blacklisting. You can also use asterisk, let's say, exclude everything. Or exclude everything starting with whatever. Did someone else got measurements, results? What was it? 16 seconds, something like this? Okay. Feel free to go to the next step. So if you like, we have 20 minutes more. Let's, yes.
So this, these big files, for example, before it said, now it says like 660 megabytes. Where are they stored? Are they in this cube file?
This 600 megabytes will be stored if you enable tracing. At the moment, we didn't enable tracing. We only enabled profiling because we don't want, like, you never start from scratch with tracing. It's dangerous because it's like can overblown. You can collect gigabytes or even terabytes of data, and it's if the data is polluted at the moment. So we don't want to investigate. We want to first get a clean data. Once we have a clean data, we can analyze it, enable tracing. And this 600 gigabytes will be collected once we enable tracing. Like, not sure if we can reach this point, but it is all described here. And you can use this website and try like later. It's like not like we are already approaching. So, and basically, if you finished, you will see inside this Scorpio directory many files. And Cubics file is this file which collects the profile. Actually, profile, it's called profile.cubics. The rest is Scorpio.cfg includes all the parameters which were used during our measurements, and you'll see if this particular variable was set or not. Now, I hope you all installed Cube and you collected already data, like you downloaded data in advance. You can actually go to your laptop, not on Bridges, and open Cube files on the Bridges. I would recommend to open Square. I didn't mention, like, if you go to the Explore profile with Cube and execute this command, it will create. This you should do on Bridges. If you execute it on Bridges, it will create. Does the post processing post-processing means it analyzes the Cube files and creates additional hierarchies. And creates additional file, and the file will be called summary.cubics. And this file should be available on your, if you downloaded measurements already, it should be available. You can, but it will be horribly slow. Like it is installed on Bridges. You can use it, but I highly discourage you to use it. Like if you are very patient, do it. I'm not, sorry. All the measurements I already did, and I already provided as a measurement. Did you copy all the measurements before? No? Okay. Yes. Okay, then you can do it. Or just watch what I do. then you can copy it later and navigate. So, and if you open summary.cubics in your cube file on your laptop, you should see something like this. Did you open on your laptop again? Did you manage to open? No? Okay. 4 hours? Yeah, that's why you can also SCP, but it wouldn't be faster. Like from, you can all those. Ah, you're trying SCP now? Okay. Okay, let me show how you can work with the cube files. You can basically you have measurements, you have cube, you can play with it later once you downloaded it after 4 hours or 14 hours. So it's 3 panes. First pane is a metric pane. It includes time, visits, and so on. Second pane is the execution of our code. It's basically main and so on. We can see a hierarchy of our application. And the third pane is hardware. So we will see that our application was executed on 2 nodes on bridges. And on each node, we use 2 MPI ranks. And each MPI rank used 6 OpenMP threads. And data is aggregated from right to left. So if you so what basically we can see now. Let's let me collapse like this. So basically we see time, like the total time. If we summarize all time across all threads, we'll have 800 seconds. Then we will see the breakdown that we'll spend time in multiple functions, but most of them are negligible, but 2 are significant, like ADI. This is mostly probably of our interesting function. And inside ADI, we have xsolve, xsolve, ysolve, and zsolve, and computer right-hand side. So basically, this ADI is probably our solver loop. And we can see how time distributes across. First, we can look at the node level. So we can see that on one node is a little bit slower than another. And then we can see breakdown, how it is breakdowns across MPI ranks. And if we go even further, we will see how it is running across OpenMP threads. You can also expand or collapse all and see all how time is distributed. But you can imagine if you have a million threads here, it would be like long scroll. What a cube provides is the statistics about this particular, like this time in ADI, and we can see the distribution of time. So the max time was 16 seconds, and the mean time was 13 seconds. So you can see how it's balanced or not balanced. So basically, this is a typical identification, how you can identify imbalance in your application. This is easy one. Then in time, you can see after post-processing, you will see that how much time you spend in computation and MPI and OpenMP. So most of our time was spent in computation. So we can also check in which functions. It's again ADI, and in ADI we have these 4 functions. And we can go further and see that it's actually the work was done in OpenMP parallel region. Yeah. And if you are interested in where we spent most of the time in MPI, we can also look here, and it was in this exchange QBC. And we can see that most of the time was spent in MPI wait all. Like there is also additional hierarchy, how much time we spent in management, synchronization, communication, and so on. And the same about OpenMP. Synchronization, we spent significant time in barrier, and it was implicit barrier. And you can also track it down where exactly in the source code it happened. Yes, here. Did anyone manage to open Cube? Okay. At least some. Good. Good. It wasn't too slow. Okay. Then, yes. Be patient is always good, yeah. But could you follow, click as fast as I can? Okay. Okay, but at least it opened. Yes, good. Do you remember I also mentioned POP project, and it provides some metrics with efficiency and inefficiency. It can also be calculated within the cube if you go to general. And then you will see this POP, it's called Cube Advisor. And here you can investigate, for example, how efficient or inefficient your application is, or a particular function. It is here, you see, general. If you click on general, you will see the POP metrics. And let's say we were interested in ADI. And so we select functions which we would like to investigate, and we click recalculate. And it shows three metrics: load balance and communication efficiency. So basically, it means 1 is perfect, 0 is worst. And it means our application is pretty balanced, and the communication is a bit bigger than usual. I don't know, not like usual, but it's still negligible. And you can also check it for other functions. Like here, for example, you can see that the communication is really significant here because we already identify here that we spent a lot of time in MPI wait here in this function. That's why communication efficiency is not super good here. All right, so you will have some time to play around later with Cube. I don't want to spend, like, it requires some time to understand how to interpret this. Like, you can also change the dimension. Like, you can swap these panes, and then you'll have different dimensions. You can also see the source code. I didn't copy the source code, but you can also, for example, click here, and then you can see where it is happening in the source code. Because we just copied measurements, but we didn't copy source code, it is still looking for the measurements on bridges, but I'm on laptop. That's why we don't see it. We also see how it was configured, and so on. So it's a very powerful tool. You can also understand more or less structure how your application works only with a profile. For example, if you look into the visits, you will see, if you open, by the way, I forgot to tell that. If you open, there is a notion of exclusive and inclusive values. So if we open, we will see how much this BT function was called. It was called 8 times for each MPI process. But if we collapse it, it will be like very significant because all calls happening in the inside will be also accumulated. It's exclusive and inclusive times values. So and going the way like this, you can also track how your application looks like or behaves. Of course, it's not so easy as with traces, but you can also work with the profiles at the very beginning. Okay, let's go back to the website because we have 8 minutes left. We would like to enable Skalaska trace analysis. Go back to bridges, please. You remember we had this Scorpi total memory, 95 megabytes from the scoring. And I ask you to remember this. We would need this value to collect the traces. So then we follow all these rules. And then we copy batch script for Skalaska trace analysis. It's located in job script bridges to skalaska.sbatch.c.8. What are the changes here we need to do? So basically, we use filtering file, the same filtering file as before. We use here should be 95 megabytes. So in your case, it's please check that it's 95 megabytes. Here it's typo. Is it the same in the batch script? Is it 27 or it's 95? 95. Okay, then it's typo here. And then you need to put, instead of MPI run, you put prefix Skalaska analyze -t, which will enable tracing. And then you have to submit it. So what will happen behind the scene, your application will run again, will collect the traces, and then the traces analysis will be done immediately after finishing, your job has finished, and then the trace analysis will be also done in parallel. And once you're done, you'll get a lot of more files. You'll have a different directory. It will be scorp underscore bt minus mz and at the suffix trace. And there you will see a lot of files. Especially you will see the scout.cubex file, which includes trace analysis. And you'll see a lot of files related to traces, traces.otf2, definition files, actual traces, and so on. Yeah, and if you look in the Scout log file, you will see that Skalaska trace analysis has run successfully. It opened archive, it analyzed it, and collected the data, and created additional file. Then we can post-process the data with square command. This is, as I said, it's a convenience command provided by Skalaska. It creates additional hierarchies in the cube file. And yes, we are done. And I can open it on my local machine. And what we can see additionally here to previous metrics. It looks very similar to the previous run. But if we look further, you will see these frames. And there you will see inefficiency patterns, which we described before, like late senders, late receivers. And if they are marked with frames, it means that like something is detected by Skalaska trace analysis. What are these metrics? You can look into the documentation. Yes, it's like, if you click, you can read about these metrics, what is actually describes. Again, critical path is also here. You can see. Again, I remind, in a critical path indicates what you should improve if you would like to improve your runtime. You should look into these functions which are marked, which are on the critical path. What is not on the critical path, don't waste your time. And delay analysis is also here. You can also check where is most of the delay is. For example, if you look at the late sender, you will see where, if you would like to improve late sender, like get rid of these late senders, you should probably look into these particular functions which are marked here. Okay, and last but not least, Vampire. If you have copied the data, and it's a lot of data for traces, you can also open the traces with Vampire, because we already collected the traces once we did the Skalaska run. And now we can visualize them. If we open Vampire, I'm not sure, because it is for you it's a demo license. It might be restricted for some time, or just play around once you install it, because it's like, I don't know, it's week or months, depending on the Vampire restrictions. But this is basically what you should see. Yes. Yeah, this is how results of the trace collection look like. Yes. Yes. You can SCP it, or it is also possible to download it with this Cybo. Like, I also provided link where you can download it from Cybo. Yes. To see where, in traces or in profile? Here I usually use fit chart height, and it will be fit to all the threads will be visible here. Yes, and all are visible here. Yes, of course, if you have millions, it will be like very distracted, maybe. Like, it depends. It depends. You can also filter some functions here. It is very flexible. You can filter what you want. You can also collapse here. For example, you can see only MPIs. Okay. What is also I like to see here, it's a call stack. For example, you can see what is exactly what's going on the process 0, let's say. We have a function BT, and inside BT we have these multiple ADIs. You can see the basically structure, what's going on the process 0. And you can relate it to the total timeline. And there are many other options, like communication metrics and so on. Okay, yeah. So I would like to wrap up. So basically, this is a sneak preview how to use tools. It's not easy. Like, you have to adjust your workflow to this particular tool, and it depends on what you want to learn about your application. About, like, first you need to understand what you want. Then second you understand which tool can provide this information, if there are any, and then learn how to use it. And the most difficult part, how to interpret the data. Like, collecting the data is also difficult, but interpreting the data and finding something is even more difficult. So that's why I would recommend you to approach experts from POP or EpiQ. I put also some flyers here. Feel free to take them. Also, you can feel free to contact me if you have some questions. So thank you so much.